With this learning objective, we are going to begin a whole new world of heterogeneous equilibria. We're leaving behind the acid-base equilibria that we have done all the way through the previous unit with Dr. Solt and the first several learning objectives of this unit. We are now ready to enter a world where there will be a solid and an aqueous solution, both combined, and we are going to be studying the world of insoluble salts. We're going to learn how to write the reaction for the dissociation of these insoluble salts. We call it a solubility equilibria. We're going to write the equilibrium constant expression for these reactions, which we call the law of mass action. And so let's begin by talking about insoluble salts. Earlier, now when I say earlier, I would mean before you ever even began working through the lessons with us, you would have learned about insoluble salts, how some salts are insoluble. You learned laws or rules to help govern which salts are soluble and which salts are insoluble. But when you have these insoluble salts, it does not mean that nothing dissolves in solution. It means that just a very, very tiny amount will dissolve. So we're going to have an equilibrium exist between the undissolved salt and the small amount of salt that does dissolve. And that's what we're going to be considering in this learning objective and the next several throughout the rest of this unit. So here's an example of an insoluble salt. It's silver chloride. When it dissolves in water, we're going to be able to write this reaction. We have, and this is the way we always will write it, we will put the solid on the left as a reactant, and we will put the ions it breaks apart into on the right as products. Now this is a reversible reaction, so it could be written the other direction, but we never will, because when we start studying this process, we're going to be using equilibrium constants that we can look up in tables, and they always apply to the reaction written in this fashion. So if we have that reaction written up at the top, you should be able to write the equilibrium constant expression or the law of mass action for this reaction. So choose the right answer. Well, if you selected answer B, then you are correct. We would not include the silver chloride in this because it's a solid, and you never include the solids when you write these expressions. This equilibrium constant, we're going to give a subscript of SP. So we've seen Kas, we've seen Kbs, we've seen Kws, we've seen Kcs and Kps. This is KSP, and SP stands for solubility product because it is a product of the ions that have been dissolved into the solution. There is a table of solubility folders, solubility products provided for you in your resource folder for this MOOC, and you'll be able to look up values when they're needed. So once you have one of these equilibrium constant expressions, we can do all the same types of calculations we've done with any other equilibria problem that we've seen throughout the units that we've been covering on equilibria. So let's try one. No, let's not try one. Let's work on this guy and practice writing our expressions. Here's a reaction. It's magnesium chloride. The first thing you need to be able to write is the reaction itself. So remember, you put the solid on the left and the ions it breaks apart into on the right. You give it a try. Did you write this? Did you remember that there are two chlorides and not write it as Cl2? It is not the element, it is they are the ions, the monoatomic ions. So you have two of the Cl minuses. So once you have that, you would be able to write the expression, the law of mass action for this reaction. Okay, so hopefully you tried it out and you wrote this. It has the SP for the solubility product, and we would have the magnesium to the first power, and because there's a 2 here, we would have the chloride to the second power. So this is the end of our learning objective number 9. It was a very short lesson, but I would like for you to be able to take any insoluble salt and write the reaction, which we did here in this problem, and also write the equilibrium constant expression or the law of mass action for that.